Okay, so let's try actually using some exponential models today. So instead of just total theoretical, let's see what it looks like if we try and make some sort of a practical application. So sometimes real life quantities increase or decrease by a fixed percent each year or some other time period. The amount y of such a quantity after t years can be modeled by one of these equations. So the growth model, we got some coefficient a. Notice that our independent variable is going to be t instead of x. Right, we'll plug in a number for time and then we'll get our value y afterward. And the growth model is when we're going 1 plus some rate r. Decay, of course, will be 1 minus that rate r. A is the initial amount we start with. R is the percent increase or decrease written as a decimal. 1 plus R is a growth factor. 1 minus R is a decay factor. So, brand new car, or any car we purchase, I guess, can be approximated by the model y equals 25, 0.85 to the t, where t is the number of years since the car was new. Okay, is it growth or decay? Well, 0.85 is greater than 0, but it's less than 1, so it's decay. Percent increase or decrease? Well, one takeaway, 0.15 is 0.85, so we're going down by 0.15 a year, or 15%. I know the car be worth just 8,000. Well, trace function of some type will show us it's been about 7 years. After 7 years, that $25,000 car is now down to just $8,000. A real life situation with world population. We write a growth model. And then after we make the model, can we estimate the population from 2005? Well, we start with 6.09 billion. 1.18% as a decimal, 0.0118. So for A, we plug in 6.09. For R, we plug in 0.0118. So there's our equation. So 2005, plug in T is 5, we get about 6.46 billion. When is the population 7 billion? Use a table feature. Compound interest. Okay. So, for example, I deposit money in the bank and they pay me interest at the end of each month, or they pay me interest at the end of each quarter. So it's dropped $9,000 in account, 1.46% interest. Find the interest after 3 years when it's compounded quarterly. Of course, quarterly means 4 times a year. Again, principal P, we deposited 9,000. Rate, Remember, I got to change that 1.46% to a decimal. And of course, it's going to be 4. Time is going to be 3 years. I'll probably simplify that up a little bit. I could have done the 4 times 3 is 12. Grab a calculator, pound some buttons, kapow. Okay, now this is a slightly fictional, but relatively close to real life. Worth A, well, $27,000 for that new home. That median home, I should say. Right? Well, there it is as a decimal. So there is our model. I can simplify that. Well, what was the median home value in 1980? T would be 10. We're looking at a little over 50,000. You're like, no way. We went from 27,000 to 50,000. Well, using this model, what would 2019 be? That's 49 years after 1970. About 590,000. When will it be worth $1 million? We don't yet have the skills to solve that. So we'll just do a graph. Comes out to be about 57. In class, we'll take a look on Desmos, how I'm getting that 57. I neglected to I gotta go back and edit this compounded monthly. Right? I didn't put that in here. In class it'll work, but on this recording it's embarrassing that I didn't say it's compounded monthly. So 1.5 would be 18 months, because it's 1.5 years. I got $5,190.86.